And this denominator in this multiplication by 2, I just filled this in, n dot k for our point xi star yj star is just the expression for the normal vector, which is written pretty small here. You might not be able to read it, but it's just this expression with the xi and the yj substituting for the x and the y. And then that's dotted with k. Well, the I dot k is 0, j dot k is 0, k dot k is 1, so what we end up with is this term, which I've written out a little bigger right here. And that's going to be our denominator. Now, if we divide by this, it means we multiply by the reciprocal, so we multiply by 2 divided by this, and this is our result. So this is the contribution to the flux from the ij area increment. We sum this expression, which is written a little more clearly here, over I and j, and that sum is going to then represent the total flux and I realize I didn't write my delta x, delta y on this term. Hopefully that was bothering you, but hopefully that corrects it. So again, we sum that expression over I and j, and then we take a limit and we get this integral. So this integral now represents the total flux through that surface, total flux of the gradient of our original scalar function through the hemispherical region. The limits on the region, and this should be very familiar from previous work. If you thought you saw a lower limit of 0 here, you were right, but that's not correct. The circle in the xy plane is described by x from -2 to 2, y from negative square root of 4 minus x squared to the square root of 4 minus x squared, and that's something to be very familiar to you. I'm not going to explain it again. The alternative way of writing the integral, we could reverse the integration, and we could let y go from -2 to 2, not from 0 to 2, from -2 to 2, with x going from negative square root of 4 minus y squared to the square root of 4 minus y squared. Okay, now the integrals appear to be correct. And down here I do note how we got these two sets of limits. Okay, I said I wasn't going to do that, but I did. The region is -2 less than or equal to x less than or equal to 2, corresponding to this integral. And for x between -2 and 2, the y range that describes the region is from x equals 0. And this picture isn't even right. Hang on. Okay, this isn't very well drawn, but I've kind of drawn the lower half of the circle. Because this is a circle in the xy plane, I drew a semicircle because we're integrating over a hemisphere, but that semicircle would be in the xz or the yz plane. That semicircle is above the xy plane. So within the xy plane, very clearly, we have a circle. In other words, we look here, we have the circle in the xy plane. It's that circle that's partitioned, and that circle is described by x from -2 to 2, and then y goes from negative square root of 4 minus x squared to the square root of 4 minus x squared. And I made a correction. Y goes from the negative square root of 4 minus x squared down here to the square root of 4 minus x squared up here. On the y description, the y value goes from -2 to 2, not 0 to 2, and the x goes from negative square root of 4 minus y squared to positive square root of 4 minus y squared. We're not going to go through the details of the integration. The integrations use techniques that we've seen a number of times already. You're going to have to use some trigonometric substitutions. The integral of -2y over this denominator could be integrated by letting u equal y squared, du equals 2y dy. So those tricks can be helpful, but you're going to end up separating this into three integrals. One where you have 8 divided by this, another where you have minus 2y divided by this, another where you have minus 2y squared divided by this. In two of those cases, you're going to let y equal some constant times the sine of an angle. And that's a basic Calculus 1, first year calculus type of trigonometric substitution, an integration technique from second semester calculus, which we've gone over in the process of doing multiple integrals. So if you need to review the idea, it's there. You can look up trigonometric substitutions on the web, a variety of resources where you can see how to do this integral. Now, though I'm not going to go through the steps of integrating this, I'm going to let a machine integrate it, but before I do, I'm going to make an estimate. Based on this picture, it appears that the flux through this surface is you got more flux going out of the surface than you've got going into the surface. And here the flux is pretty much in the same direction the surface, has magnitude 2. Here the flux is largely in the direction of the surface, and it has a magnitude greater than 2 because remember that the I component at this point is 4. Now over here we have flux going into the surface, so that the average magnitude of the flux appears to me to be certainly greater than 1. It appears to be going out of the region, and it appears to be probably on the average, because remember that these vectors are not always exactly parallel to the normal vectors, probably not a whole lot greater on the average than 2. So I'd make the following estimate. Average flux per unit area maybe something around 2. Now that's with a large that's an estimate. Now what's the area of the hemisphere? Is 1/2 the area of the whole sphere. The area of a whole sphere is pi r squared. R is 2, so that's going to be 2 pi times 2 squared, which is 8 pi. Accordingly, the average flux out of the sphere is about 2, and the area of the sphere is 8 pi. I estimate then total flux may be around 16 pi. I don't have a whole lot of confidence that's a real accurate estimate, but if I get something that's drastically different than 16 pi, I've got to either rethink my picture or rethink my integral. Now I'm going to step away for a minute and throw this integral into a computer and see what we get. Now it's not that we can't do this. We could go through the steps of this integral, but in the interest of time, I'm going to fall back on machinery to give us an accurate result. Okay, kind of double check this on the machine because the machine had a little trouble doing an approximation to the integral. It had to do the actual integral. I don't know why it had trouble doing an approximation, but what the computer gave us, this integral is 32 pi over 3. Now that comes out a little more than 10 pi. The estimate was 16 pi, so I did overestimate the amount of flux. We have flux coming out of the region, we have flux going into the region, and I suspect I underestimated the amount of flux going into the region. So that the average rate at which flux leaves the region is about a little less than 2. The integral is 32 pi over 3, and the total flux estimate Remember, the estimate was based on just my numerical sense and my drawing, none of which are all that accurate. Okay, so there's reasonable agreement between the estimate and the actual, so that the actual result appears to be very reasonable, and we expect that it's valid. It's a good exercise in integration to go ahead and attempt to do this integral. Again, it doesn't require anything but some trig substitutions and some u substitutions. But there's a lot of detail, a lot of algebra to be worked through. Good practice.